Good morning, everyone. My presentation today is titled Smart Greenhouse Irrigation and IoT-Based Approach. This project was carried out by our team from the Department of Electrical Engineering, Polytechnic Unggoma. The members of the group are Muhammad Hamizan Razi, Farhani Muhammad Fauzi, and I am Kaumanyin, the team leader and the presenter for today. Now, let us begin with the background and the objectives of this study. Agriculture is critical for food security, but traditional irrigation often wastes water and relies heavily on manual monitoring. IoT provides an opportunity for real-time control and automation. Therefore, the objectives of this project are threefold. First, to develop an IoT-based greenhouse system. Second, to implement automated irrigation and temperature control with manual override via the Blink application. And third, to evaluate the system's scalability across different container sizes. Proceeding to the next part, I will explain how the system operates. This flowchart shows the operation of the system. It works in two modes, automatic and manual. In automatic mode, the water pump activates when soil moisture falls below 20%, and the fan turns on when the temperature exceeds 30 degrees Celsius. Moving on, let me share the hardware and IoT integration. The system uses an ESP32 microcontroller as the central controller. Sensors include the DHT element for temperature and humidity, and a soil moisture sensor. For the fan, pump, relays, and LCD handle activation and display. IoT connectivity is provided by the Blink app for real-time monitoring, notifications, and manual override. Next, I will describe the experimental setup. For testing, we use a prototype planting container measuring 32.5 by 46.5 by 10 centimeters, giving about 15 liters of loam soil. To check scalability, we also test two commercial containers, one with 59 liters and another with 4 liters of soil. Let us now proceed to the experimental results. In the prototype container, about 3.8 liters of water were needed to restore soil moisture. The theoretical pumping time was 1.3 minutes, while the actual measured time was about 2 minutes. The system maintains soil moisture within the recommended 15 to 25% range. Now, let's continue with the scalability results. Scalability testing showed a linear relationship between soil volume and pumping time. This confirms that the system can adapt effectively to both small and large containers. The graph here illustrates this trend clearly. Next, I will highlight the usefulness, novelty, and commercialization potential of the system. This system is useful because it reduces manual work, saves water, and allows real-time monitoring through the Blink application. Its novelty lies in combining irrigation and temperature regulation in one system, with both automatic and manual modes validated for scalability. Commercially, it has potential as a low-cost greenhouse controller, a DIY kit for urban farming, or even as a teaching aid for polytechnic labs. Finally, let me conclude this presentation. In conclusion, our IoT-based system successfully regulated soil moisture and temperature, proving efficient and scalable for greenhouse application. Future work will focus on predictive control, solar integration, and multi-sensor improvements. We would like to thank Polytechnic Unggoma for their support in this project. That ends my presentation. Thank you very much.